Polynomial functions have these multiple terms within those polynomials. So with this polynomial that's given to you, you have the 3x to the 5th power, which is a term. The 6x to the 4th power is a term. The negative 2x cubed is a term. The x squared is a term. The 7x is a term. And the negative 6 is a term. Within these terms, you have different parts. You have a coefficient, which is the number that's in front of the variable. So for that 3x to the 5th power, the coefficient there is the 3. You also have a leading coefficient and a leading term. The leading coefficient is attached to your leading term. Your leading term has the highest degree. Your degree is the power. So let's just say we're looking at this 3x to the 5th power. That power is 5. So the degree of that term is 5. Because it's greater than any other power, that is your leading coefficient with your leading term. With these, if you have something like x to the 2nd, y to the 3rd, you would add those powers to get the total amount that is your degree on that term. Okay? With this slide here, it just gives you different polynomials with examples of your degree, your leading term, and your constant term. That constant term with any of these polynomials is the term that does not have a variable or a letter attached to it. It's just the number. And you'll realize with any of these, that sign that's in front of the number stays with the number, or the sign in front of the term stays with the term. For these, you have different types of polynomials. This one that they give you underneath your table is just one single term, which is called a monomial. You have other different polynomials like binomials and trinomials as well, where a binomial is 2 terms and a trinomial is 3 terms. Like we went over yesterday, different functions have different lines or different types of lines. You're used to seeing linear functions or square functions where the linear function is just a straight line. If it's positive, it goes up from left to right. If it's negative, it goes down from left to right. And also, if you look at something like x squared, that's that u parabola there. If there was a negative in front of that x squared, it would just open down instead of opening up. With these, you are going to start looking at end behaviors. Your end behaviors are what's happening to that line at the beginning and at the end of that line. So if you look here, these are there's arrows on each of these lines. So it just tells you that it continues to go on for forever. So if you look at y is equal to x squared, you have an end behavior here that both of these lines are going up. So they are both rising to the left and rising to the right. So you can say that it's just rising left and rising right. We're going to get into end behavior notation as well, which this rising left, rising right will help you to understand. For something like y is equal to x cubed, you have this squiggly line, and your line, again, is going up as it goes to the right, down as it goes to the left. So when you look at your end behaviors for an x cubed, what's happening as it goes to the left? Well, that line is going down, so it's falling left. What happens when it goes to the right? It's going up, so it's rising right. For that D example, so y is equal to x to the 4th, you have a u-looking line as well. So you'll see here that this is odd, or this is even. Your power here is even. So we're going to do the same thing that we did with the other one. Those end behaviors are going up for both. So end behaviors, you're going to the right as you rise. So it's rising right, rising left. For example, E, we have y is equal to x to the 5th power. So again, we have that squiggly line. Again, one side goes up, one side goes down. If you look here for ending behaviors, what happens as it goes to the left? It's falling. So you can say that it's falling left. What happens as it goes to the right? It's going up, so it's rising right. You'll realize with these about your powers. Look at the powers. You can look at the page before this too to give you a good idea or an example as well. We had x squared on the page before, and it looked kind of like x to the 4th power, but it was more narrow. Whenever you have a power that's even, so 2, 4, 6, your end behaviors are both going the same way. Whenever you have an odd power, those end behaviors are going opposite ways. So 3, 5, 7, those are opposite powers, those are odd powers, so your end behaviors would be opposites. So you might want to make a little note down here. Even power, same end behavior. Odd power, opposite end behavior. Okay. Look before this, that x to the 4th power, it's similar to x squared, but it's just widening a little bit. So it becomes to where that graph gets like a stretch is happening. If we look at x to the 3rd and x to the 5th, what's happening in the middle of that line? It's stretching, so it becomes to where it. Okay, so it tells you with these that as your degree gets bigger, those graphs end up becoming flatter. So if you, it's flatter. If we look at example 1, before we actually graph these, we're not going to worry about graphing them. We're just going to tell about the end behaviors based off of the transformation. So for example A, we have p of x is equal to negative x cubed. Well, what type of graph is that x cubed? Or it's an odd power, so it's opposite end behaviors. We do have a negative though, so that negative we reflect across the x-axis. So if these were opposite behaviors, originally started like this, we're going to flip it so that way it opens to the, or it goes up to the left, down to the right. So what are our ending behaviors here? For our ending behaviors, we're going up and to the left, so we're rising left. And to the right, we're going down, so that means we're falling right. So that end behavior is like the most important part with these examples that we're going to go over now. For example B, we have q of x is equal to x minus 2 to the 4th power. This minus 2 here means that we're going to the right 2 units. This 4 is an even power, so we have the same end behavior. So we don't have a reflection here or anything, so this is still going to be opening up. So what's happening with our end behavior? Where are these lines going to? Well, as it goes up, it continues to go to the left, so that's going to be rising left. And as it goes to the right, it's also going up, so that's rising right as well. For example C, we have r of x is equal to negative 2 x to the 5th power plus 4. Well, think about this. You don't even need to worry about graphing this or finding the transformations really. The only thing you have to check for is that reflection. So you see that there's a reflection here, so it does reflect. So we want to think opposite. we have an x to the 5th power, so that power is odd. So our end behaviors are going to be opposites. Think about the way that a graph of x to the 5th power looks. We have opposites, but we are reflecting. So we're looking at a graph that opens to the left and up and goes down and to the right. So for our ending behaviors, as we go to the left, it goes up, so that's rising left. And as we go to the right, it goes down, so that's falling right. So these ending behaviors are to help you with looking at your ending behaviors in ending behavior notation. Before we get to that, we're going to be looking at continuous lines. Sometimes with these lines, they will break or there'll be a hole in them. When that happens, they're not a function. So you're looking on whether or not these graphs are continuous. If we look at the first example to the left, because there's these corners and these cusps here, so these literally like really sharp curves, this is not a function because this is not continuous. The middle graph, we have a continuous function here. Yes, there's curves there, but those curves are smooth. They're not pointed or blunt with these peaks or anything like that. So this one is continuous. Same thing with the graph on the right. Those curves are smooth. We have a continuous line here, so we're good with that one. So your end behavior notation, we're going to switch this up a little bit. Your textbook goes over it as y to infinity as x to something. We're going to focus on x behavior first, though. The reason why is because as we're going right or left, that's how we're getting that falling or rising. So we're first going to look at the x values and see where the line goes based off of those x values. So with any of this, you're looking at the end behavior like we were dealing with. So let's just say your end behavior was rising left, rising right. So this is obviously an even power function like we have here with the y is equal to x squared. If this is what our ending behavior was originally, to put it in end behavior notation, we're going to say as x goes to negative infinity, y goes to what? Well, think. If x is going to negative infinity, so it's going to the left, what's happening? It's rising, so it's going to positive infinity. So that infinity would just go inside the box there. Then you would go for x to positive infinity, y does what? If your x value is going to the right, what happens as it goes to the right? It's rising, so that again is positive infinity. If you have opposites, like if we're falling left, rising right, we would say as x goes to negative infinity, y goes to where? Well, as we're going to the left, what's happening? We're falling, so that's positive infinity. Then we also have as x goes to positive infinity, y goes to where? Well, as we go to the right, we're rising, so it's going to positive infinity. This should be a negative. Top one here. As we go to the left, we're falling, so that's negative infinity. So if we look at some of these graphs, for this first one here on the left, we have a graph where our ending behavior is happening based off of where these lines are continuing to go to. So if we look to the left, what's happening with that line? It's going down, so this is falling left. If we go to we look right, that line's going to continue to go up, so that's rising right. To put this in end behavior notation, look at what they give you. As x goes to negative infinity, where are we going with y? Y goes to negative infinity because it's going down. And as x goes to positive infinity, y goes where? Well, it's going up, so it goes to positive infinity. For that second graph that we see there, look at your ending behavior. On the left, that line's going up, so we have rising left. On the right, it's going down, so that's falling. Right. Look at your end behavior here and find your end behavior notation. So as x goes to negative infinity, what's the line doing? It's going up, so y goes to positive infinity. And as x goes to positive infinity, so it goes to the right, what's happening with our line? It's going down, so y goes to negative infinity. For that middle and to the right example, you have two of these end behaviors that are doing the same thing. So they're both going up. So we are rising right, rising left. So as x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to positive infinity as well. And lastly, that one that's to the far right. Those two sides of that line are both going down. So again, we have ending behaviors that are doing the same thing. So the ending behaviors are both going down. So falling left, falling right. So if we put this in end behavior notation, as x approaches negative infinity, y does what? It goes to negative infinity. And as x approaches infinity, what does y do? Y approaches negative infinity as well. If we look at example 2, that's not done for us. We're just determining the end behavior of the polynomial. So we want to start with transformations. You have a negative here, so we know this is a reflection across the x-axis. From there, look at the highest power that you have there. So the degree of this polynomial tells you what type of polynomial or line you're going to have on that coordinate plane. Your highest degree is 4, so it's even. Our end behavior is going to be the same. So we're either both going to be rising or both going to be falling. What happens when you reflect? It opens down, so we're both going to be falling. So for your end behavior here, we have falling to the left and falling to the right. So from here, the only thing I have to do is give my end behavior notation. So as x goes to negative infinity, we are both going down. Y is going down as well. Y goes to negative infinity. And as x approaches infinity, y approaches negative infinity again. So the only thing that's going to happen here is literally that y is going to, something is changing. Your x approaches negative infinity, as x approaches negative infinity as x approaches negative infinity is never going to change, and as x approaches infinity, that's never going to change. The only thing that changes is that pink part of these two end behavior notations. When solving these polynomials, it's the same exact thing as using zeros or finding the zeros. The only thing you have to do is factor that polynomial in order to get what your zeros are or what x is equal to. In this example that they give us, that they factor for us, we have x squared. P of x is equal to x squared plus x minus 6. Change your p of x to be 0. Then factor your trinomial. If it's something like x cubed plus x squared minus 6x, you're going to have to factor out your greatest common factor first before you continue. Once you factor, you would set each part of that binomial times the binomial equal to 0. So in this case, that x minus 2 gets set equal to 0, and that x plus 3 gets set equal to 0. And we would just solve for both of them. So we would add the 2 to each side and get that x is equal to 2. We subtract the 3 from each side, we get that x is equal to negative 3. With these, we can also tell what our end behavior is too. When we look at this graph, we have an even power, so we know our end behavior is going to be the same direction for both the x approaches negative infinity and x approaches infinity. We don't have a reflection here because there's not a negative in front of our leading coefficient, so our ending behavior is going to be the same. And then we're going up for both. We're rising left, rising right. Oops. So this just tells us that as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches positive infinity as well. Because it's a 2, it's an even power, so they're going to have the same positive infinity for both parts of your end behavior notation. If we look at our next example, it just tells us to find the zeros of P and sketch a graph. We're not sketching the graph, we're just going to find the zeros and tell the end behavior notation. So we have P of x is equal to x cubed minus 2x squared minus 3x. First thing we do, turn that P of x to be 0. So 0 is equal to x cubed minus 2x squared minus 3x. From here, factor. That x cubed minus 2x squared minus 3x has a greatest common factor of x. So I can factor out an x from all of these first. It's going to leave me with x times x squared minus 2x minus 3 is equal to 0. From here, find your factors of that negative 3 that add up to be negative 2. That negative 3 is 1 and negative 3. That'll give us that negative 2 that we're looking for. So this is x times x plus 1 times x minus 3 is equal to 0. Now that we've factored completely, set each part equal to 0. So x is equal to 0, x plus 1 is equal to 0, x minus 3 is equal to 0. If we solve that x plus 1 is equal to 0, we just subtract the 1 from each side and get that x is equal to negative 1. If we add the 3 to both sides and then x minus 3 is equal to 0, we get that x is equal to 3. So we have x is equal to 0, x is equal to negative 1, x is equal to 3. From here, we still need to find our end behavior notation. So looking at that leading term, the highest degree or the highest power is at 3, so it's odd. We're going to do opposite directions. So think about this. This line would look similar to this. So our end behaviors are going to be opposite. Oops. So as it goes to the left, what happens? It falls. So we say it's falling left. As it goes to the right, what happens? It goes up. So it's rising right. So to put this in our end behavior notation, again, that as x approaches, I'm going to do negative infinity first. Negative infinity, y approaches what? And as x approaches positive infinity, y approaches what? We're just filling in those boxes. So we said to ourselves, these are opposites. One of them is going to be negative infinity, one of them is going to be positive infinity. As we go to the left, it says that we're falling, so that's going negative infinity. And as we go to the right, it says we're rising, so that's going positive infinity. All right, so the last part that we're going to go over is multiplicity, which is, if you had me for Algebra 2, something I definitely went over 2 years ago. I don't know if we got to it last year, but multiplicity is the amount of times an answer occurs. So with these, you're going to have a part or a set of parentheses raised to a power. That power is the number in your multiplicity. So when we look at these parts of this function, for this example, we have x to the 4th power, we have x minus 2 cubed, and we have x plus 1 squared. So this x to the 4th power we can write as x in parentheses raised to the 4th power. That x minus 2 is raised to the 3rd power, and that x plus 1 is raised to the 2nd power. Remember, this is all equal to 0. So with this, that x to the 4th power, that answer that you're going to get there when you set it equal to what's in the parentheses equal to 0 and solve, is going to happen 4 times. So it would have a multiplicity of 4. The x minus 2 to the 3rd power, when you set the x minus 2 equal to 0 and solve for x, it's going to happen 3 times. So it would have a multiplicity of 3. If you set the x plus 1 equal to 0 and solve for x, whatever you get is going to happen twice because that's squared that's on there. So if you solve all of these, we have x is equal to 0 with a multiplicity of 4, because our power is 4 on that one. For the x minus 2 is equal to 0, you would have x is equal to positive 2 with a multiplicity of 3. And that x plus 1 is equal to 0, that would give you x is equal to negative 1, and we would have a multiplicity on that one of 2. Now, you can still find your ending behavior here as well. With that power, it would just be the 4, and they would both be going the same way. There's no reflection here, so it would just be as x approaches negative infinity, y approaches infinity, and as x approaches positive infinity, y approaches positive infinity as well.